In part B, we're given another triangle to solve. So we're given alpha is 60 degrees, A is 20, and then C is 10. So if I try to draw this out, sort of in a generic triangle here, I'll call this angle alpha, so it'll be 60 degrees. A is the side opposite that, that's 20. That's the angle I'll call beta, that I'll call gamma. And then the angle opposite gamma is what I'm calling C, and that's 10. So I'm in the case here where I'm given an angle, one of its adjacent side, and then its opposite side. So it's the ASS case, otherwise known as the ambiguous case, which means there's lots of different things that could happen here. It may be that there's no triangle at all. It may be that there's one triangle and it's a right triangle. There may be two different triangles, or there could be one triangle that's not a right triangle. So we go from either having no triangles, we can have as many as two different triangles depending on what's going on. And we'll see why here in a minute. So I've got an angle side opposite pair, alpha and A. I'm going to have to work with that to find these other guys. All right. So if I'm going to use law of sines, I know I've got the sine of alpha over A equals sine of gamma over C. And I've got alpha is 60 degrees. A is 20. Gamma I don't know. That's what I'm looking for. But I know the side opposite that is 10. Okay, so this gives me the sine of gamma is 10 sine 60 degrees over 20, which is 1/2 sine 60 degrees. Sine of 60 degrees is something I know. That's radical 3 over 2. Multiply that by 1/2, I get radical 3 over 4. And this is where the ambiguity slips in. It's possible when you go through this arithmetic, you could get a number here that's bigger than 1. If I had a number that was bigger than 1, that would tell me that there'd be no solution or no triangle. Radical 3 over 4, if I want to approximate this, this is a radical 3 is like 1.7-ish over 4. So this is less than 1/2, and so certainly there is at least one angle that satisfies that. Okay, but actually there's two angles that could potentially fit inside the triangle that have this number. So I go back to unit circle. I'm going to have one guy whose sine is radical 3 over 4 in quadrant 1 and another guy in quadrant 2. Okay, and it's possible I could have two solutions to this that fit inside the triangle. Okay, so let's see if that's what's happening here. Since this is an angle that I don't know, or excuse me, this is not one of the numbers we had to memorize, I'm going to have to use the arcsine function. So from sine gamma equals radical 3 over 4, I know that one solution is going to be the arcsine of radical 3 over 4. Okay, now since this is less than 1/2, I know that whatever gamma is, it's going to have to measure less than 30 degrees. 30 degrees has a sine of 1/2, and since it's less than 1/2, it's got to be an angle less than 30 degrees. So I know that gamma's got to be less than 30 degrees. Okay, the other alternative is gamma equals pi minus arcsine radical 3 over 4. That's my quadrant 2 angle, which would be something that's going to be bigger. It's going to have to be bigger than 180 minus 30 degrees. So gamma would have to be bigger than 150 degrees. All right. So these are the two potential candidates I have for gamma. Now let's go back to my original. I'm given that alpha is 60 degrees. So given that alpha is 60 degrees, it's certainly possible that gamma is less than 30, okay? Because that would be at most 90 degrees of the triangle, and so beta would be the rest of it. But if I have an angle in there bigger than 150 degrees, there's no way I can have the other angle in there 60 degrees, because 60 plus 150 is well over 180, okay? And so even though this is a viable candidate for an angle inside the triangle, this won't fit in our triangle, okay? So this is the only guy I care about. And so he's the one then we'll proceed with as we go through the computations. Okay, so we've got alpha 60 degrees. Gamma now is the arcsine of radical 3 over 4. We have left to find beta and b. And so we can use the fact that the sum of the angles inside a triangle add up to 180 degrees. Okay, so how do we write this down? Technically, when we look at the arcsine of radical 3 over 4, this gives us a real number between -1 and 1, which corresponds then to radian measure. Okay, so it depends how fuddy-duddy and precise you want to be about this. I know that when I add up the angles of a triangle, they add up to 180 degrees, or in radians, if I'm using radian measure, that's pi. And so we've got degrees on one hand, we've got radians on the other. How can we marry these two? Well, I'm just going to use radians, and then we'll convert degrees at the end, because alpha is easy to write in radians. This is not so easy to write in degrees. So beta is going to be pi minus alpha, which is pi over 3 minus gamma, arcsine radical 3 over 4. And so this is 2 pi over 3 minus arcsine radical 3 over 4. Okay, so now to find b, I can use law of sines. Oops, I'm looking for a side, so I'll put the side on top. So b over sine of b, b over sine of beta is the same as a over sine alpha. So b equals a sine beta over sine alpha. A is 20. Sine of beta, which we'll come back to in a minute, over sine of alpha. And what's alpha? 60 degrees, pi over 3. And so b is 20 sine beta divided by radical 3 over 2, which would be 40 sine beta over radical 3. Okay, now what is the sine of beta? Well, once again, depends on how much you are allowed to use the calculator. What is the sine of beta? I'm going to use this as an opportunity to review some identities. Otherwise, you'd just be plugging stuff in your calculator at this point anyway. Okay, so we're going to do some extra work here to see what sine of beta is exactly.